not bottom of the range for an alternative microphone.
I'll move out of the way if it's distracting. Sorry.
No, it's enough. It's enough.
We're just making conversation whilst we wait for the other people.
Right. Okay. Sorry.
Yeah. There was a chat opening. Yeah. Don't worry.
At the moment, there's 4 of you. Should be at least 1 more, possibly 2.
2 more.
2 more.
2 more. Yeah. Okay. Very good. And I've been sent some stuff. So let's see if which I'm ready to share. Whilst we're waiting, does anybody have a question they want to ask that we could answer quickly?
Oh yeah.
Rex, should we stop the recording?
Yes. No, can't see. Yes. Yeah. Right.
You are not the first student to make this mistake. In fact, I would go so far as to say that 99% of students make this mistake.
Okay.
It's because they don't understand that these lines along the top are pipe lines. In fact, they're sometimes what we call ring mains. And the idea of a ring main is that you have a ring of pipe that go all the way around your little plot, and you can tap in to any point on the ring main and take material out of it. So that one doesn't exist. So let's get through it. Now, if we go backwards on this particular pipeline, notice it says 20 Celsius and 1.01 bar absolute.
Mm-hmm.
That doesn't seem very consistent, does it? They're saying it's 16 Celsius and 0.53 bar gauge.
That's not supposed to be, is it?
I don't think that's supposed to be that. I think that's a stream. Another stream's.
Well, it needs putting in the right place.
Yeah, sorry, my bad.
Yeah.
Now, look, there will be things on the block diagram like that which just need sorting out. But you've got to try and get this block diagram, pretty well sorted out very soon.
Yeah.
Okay, all right. So let me have a look at this. Okay. So who is responsible for this part of the block diagram? Is there any person who's going to confess to being responsible for this area, or
As in design? Is it in terms of design?
well, or do I just ask people at random about this? Do you all know about it?
Yeah, as a group, yeah.
As a group, okay. So let's start with Jerin. Okay, why you have got this line coming down from this is fuel gas, right?
Yes.
Why do you need fuel gas in your burner?
So what I assume what happens in the burner is you mix fuel gas with oxygen, and it and the combustion of the combustion reaction produces highly exothermic, so the flames would heat up the reaction furnace, so that partial oxidation can occur.
Well, that's the key word, partial oxidation. Do you think that partial oxidation is exothermic or endothermic?
It would be endothermic.
No, it's exothermic.
Exothermic. Yeah.
Also, not as exothermic as a fully oxidized reaction.
No, but it's enough to reach the temperature you need. You don't need any fuel gas.
Okay.
And if you do use fuel gas, it throws carbon dioxide into the system, which you have to get rid of later. So, no, you don't need any fuel gas.
So we're not considering to use HP steam.
Well, I'm coming to steam in a minute.
Oh, sorry.
I'm seeing as you're next on my list.
No.
What is this stream?
So that stream would be the return for the flue gas.
That's the return for the flue gas. What flue gas?
So initially we were planning to use flue gas for a reaction furnace. So once it gets used up in the process, I think it should go to like a return.
But
Unless
you haven't got any fuel gas now.
Oh, okay.
So why do you need some fuel gas?
So it would be condensate if we use HP steam.
Well, I don't know that you're using HP steam.
Oh, okay. Sorry. Yeah.
Are you using HP steam?
We were planning to use it.
Where's the HP steam supply?
Sorry, so we were planning to use HP steam, but then we're stuck with flue gas.
Well, sorry, I don't understand what the is in your mind here. If there's no fuel going in, there is no flue gas.
Okay.
I suspect that you're thinking that this is like a furnace. Okay?
Yeah.
In the sense that when you go into a book and look up what a furnace is, it has air and fuel going in, which burn to create flue gas, and in doing that, heats up something. This is not that kind of furnace.
Okay. Okay.
This is really just a burner with a space for the flame to be in, which we call the reaction furnace.
Okay.
And the burning and the reactions that you want are the same thing.
Okay.
Okay. So you do need the air, but you don't need any fuel gas. You don't make any flue gas. Your flue material is the process flow.
Okay. So like there's already flames inside of the burner for this specific part.
No, the burner is the piece of equipment to which the flame is attached. It is the fluid mechanical device that distributes the gases into the furnace space such that a flame will sit stably in that space.
Okay.
All right. Now, if you've ever run a gas cooker, okay, or done some camping and had a Calagas stove, then you will understand that there is a device through which the gas comes.
Yeah.
That is the burner, and then the flame sits on. It doesn't touch the burner, but it is stably. It is in a stable configuration with respect to the burner, and it sits there, and then the flame is in the right place, and then you can put your pot on top, and it gets heated up.
Okay.
All right. So the burner is a distribution device, and the reaction furnace is the space in which the flame sits, and the flame is the reaction.
Okay.
All right. You have to surround that flame with something to make sure that it doesn't burn the passing operator or some other bit of the plant. Yeah. So that's why you need a piece of equipment called the reaction furnace.
So because we're burning something, is it a good idea to use a jacket, or we don't need a jacket?
Now you're asking about the construction of the furnace. Now, in a conventional furnace, what you have is a fairly thin steel wall, and then you line it with bricks on the inside, which we sometimes call refractory bricks. And the flame then is inside the bricked part of the chamber. What the bricks do is they insulate the metal outer layer, which is what stops the gases from escaping. The metal is insulated from the hot flame by the refractory bricks, and therefore the outer skin of metal is at a modest temperature.
Okay.
And therefore it doesn't need to be made of anything very, very expensive.
Okay. Thank you, sir.
It's much easier to stack the bricks if your reaction furnace is vertical, not horizontal. You're showing it horizontal at the moment. But it's a block diagram, so don't worry about that too much until you do the PFD.
Okay.
Okay. I won't ask Ken.
Yes, sir.
Where does this water condensate go?
We were planning to use a recycle, but we found out it wasn't a good idea, so we thought to dispose that condensate.
You want to dispose of it?
Yeah, dispose it or do a water treatment to avoid environmental impact.
You want to send it to wastewater treatment?
Yeah.
Okay. You have in your brief a requirement for the cleanliness of that water. You need to be able to send it to wastewater treatment. I doubt very much that you're meeting that requirement.
Okay.
And the reason why you won't be meeting that requirement is there'll be too much dissolved hydrogen sulfide in that water. Because it's just been in contact with sour water stripper gas and acid gas.
So
How comes you can't recycle the water condensate? Is
Because it's
that
got H2S.
next to is
H2S.
Well, where are you going to recycle it to?
So can we recycle it back to the knockout?
that's what I was thinking as well.
Well then, no, water is arriving. You can't just recycle it.
Or like preheat.
It's in gaseous form, so you can't directly put it into a knockout drum.
So you can either heat it before it mixes. But then the heat duty.
but even if you're heating, what's your point of heating?
I mean, because there's H2S in that water condensate, so if we preheat it, but then the heater would have a high duty, so
It's less than 100 parts per million, so it's not a huge amount of hydrogen sulfide,
oh, okay. Yeah.
but it's more than enough to mean you can't put it down the drain or send it
So you
to
have to treat it.
treatment.
So yeah.
Okay. So, yes, you could re-evaporate it and send it through the system, right? You could do that, but then it'll turn up somewhere else because you have other places where you cool things down and water drops out. So you'll just be transferring that problem to somewhere else on your flow sheet. So you may as well deal with it. You may as well decide what you got to do about that water.
Can we dispose it?
We can't.
No,
H2S,
you're being
H2S.
told in the brief that somebody will take it. You can send it to wastewater treatment and on the refinery, provided you remove some of the hydrogen sulfide from it.
Okay.
Mm-hmm. We'll come back to that in due course. So the pressure went up by magic, Haroon.
Which pressure?
Which pressure are we talking about?
Oh, we'll see. This pressure here, you see 0.85 of a bar gauge, it says there. Do you endorse that pressure?
Sorry, 2 seconds. No.
You don't endorse that pressure. Why do you? Well, okay. What pressure should there be on that line?
It should be the same as it left the reflux drum.
Right. Very good. But if it, what is the pressure at the reflux drum, Haroon?
0.55.
0.55 bar gauge.
Yeah.
Yeah. So how does it go into the knockout drum then?
How does it go into the knockout drum?
Yeah. Knockout drum is at 0.7.
There's a valve in front of it.
Sorry, valves do not increase pressures.
So you have to put a compressor there.
You can't. It's full of hydrogen sulfide.
Yeah, sorry, yeah, that's actually dangerous. Would you use a? I don't know the answer actually. Sorry.
Yeah, I'm being very hard on you, Haroon. I'm driving you into a logical dilemma.
Okay.
Right? The gas going into the knockout drum must be at 0.7 bar gauge.
Mm-hmm.
At the moment, it's coming from somewhere where the pressure is less than 0.7 bar gauge, and you can't use a compressor.
How about if you use a pump?
No, it's a gas. Okay.
Yeah.
Something's got to give, Haroon. What's it going to be? Are you going to lower the pressure of the knockout drum or raise the pressure of the reflux drum?
raise the pressure of the reflux drum.
That is the right answer. So what's actually wrong is the pressure of the reflux drum. We're travelling a long way. Here we go, the reflux drum. Okay. So at the moment the reflux drum is at 0.55 bar gauge. You need it to be at least 0.75. Okay, but that means that this has to be 0.8.
Yeah.
Okay, which means this has to be, well, probably more than 0.87, right?
Yeah.
Which means that this pressure should be higher.
So increasing the absorption column.
But that's okay because you've got a pump.
Yeah, we can increase that pump, yeah.
We can increase that, yeah.
Yeah.
Okay.
So, column.
So we're going to Anas next.
Yes, sir.
He's quaking his boots. What will I find? Ah! Yes. See this partial condenser?
Yeah.
Okay, let's look at the temperatures around it. Okay, 200 going in. And then everything cools down apparently to 158. Yeah?
Yeah.
And we're cooling it down with this stream here. Yeah?
Yeah.
And what you've got there is boiler feed water
Yeah.
coming in and making low pressure steam.
Yeah.
And the low pressure stream is at 150. Okay. So I've got that wrong. It's okay. Okay. Right. So, Anas, see the pressure here?
Yeah.
And see the pressure there? Yeah. That's okay. But what's the pressure in the sulfur pit?
In the sulfur pit. I'm not sure.
Well, I put it to you that the sulfur isn't going into the sulfur pit if the sulfur pit is at a higher pressure than 0.25 bar gauge.
It's not actually liquid sulfur that's going to the sulfur pit vent. It's the air that's being pumped in, the ambient air. So if you scroll to the left, at the bottom of the sulfur pit, there's inlet of air at 2.10 bar G.
Yes.
So that collects up the residual H2S that might have been left in the liquid air, and then it goes through. Yeah.
But wait a minute. This air is in direct contact with the liquid sulfur. They can't be at different pressures.
Okay. Yeah. True.
Yeah.
And it must be direct contact, otherwise you won't be doing any stripping. So you, in your mind, had two different pressures for two fluids in the same compartment. That can't be right.
Yeah, but they're not mixing though, so...
They're not mixing. Well, how does mass transfer take place if you don't mix them? How do you get the sulfur out of the liquid sulfur? Sorry, the hydrogen sulfide out of the liquid sulfur and transfer it into the air if they're not in contact?
That's true.
Yeah, sure.
Okay? You can't. All right? So I'm afraid I'm right that all of the fluids in that compartment must be at the same pressure.
Okay, yeah, you're right.
Okay. Of course, there may be different pressures depending on height in the liquid, so there's
Yep.
a hydrostatic issue. But in terms of the space above the liquid sulfur, then you must have a uniform pressure, and you can't get the liquid sulfur to go into that compartment unless the liquid sulfur is at an equal or higher pressure than the pressure of the gas in that compartment. So this 1.5 bar gauge here is wrong.
Is wrong, yeah.
Yeah.
Okay. Now that creates problems around here. So, Anas, it says to incineration. Is that going to incineration at the moment?
No, that's going to the hydration reactor.
And what is the what is the biggest component of that gas flow? In other words, what is the chemical with the highest mass flow rate in that stream?
That stream, that's
this one, this pipeline here that's got pressure up written underneath it.
well, that's going to be air carrying the H2S.
Okay, right, that's fine. So it's mostly air with a little H2S, yeah? What happens when you put air into your hydrogenation reactor?
It's going to react with.
Well, it's going to blow up.
Oh.
You don't want air there.
Yeah.
No. So somehow that line is going to the wrong place.
Yeah.
Needs fixing, doesn't it?
Sorry, I initially put it to the incinerator, but then I got feedback from Dr. Demetrius saying that maybe it might be useful to pass it through the hydrogenation reactor.
Well, it might be useful to put it in the inline burner.
Okay, alright. Oh, so through the inline burner and then, okay, that makes sense.
Did I say that? I don't remember to say that.
You sent an email with the feedback.
I'll check.
Okay.
Yeah. Okay. Sometimes these messages get misinterpreted. But I don't think. I think you'll find that there's been a misunderstanding there. All right. Christian.
Yes, sir.
We've got an absorber column here, and you're putting stuff into it at 150 Celsius.
Yeah.
What's the liquid in the absorber column?
Could you scroll up a little bit, please? I just want to see them. Yeah. Oh. The stream, that's the top stream here. It's mainly vapor going into the air going into the absorber.
No, I'm asking what this liquid stream is here.
It's like, oh. I'm not too sure.
You're not too sure. Okay. All right, let's go to somebody who might be a bit sure. So we're going back to the top now. Jared, what is that liquid? This liquid here coming out of that cooler.
That would be lean amine.
That would be lean amine.
Yeah.
Right?
So amine without any.
Yeah. Okay, so that's short for what?
Sorry, the lean amine. What is it short for?
So what is the biggest component of that stream by weight?
Well, the amine that we chose was MDA, methyl diethylene.
Yeah. Okay. But you didn't choose MDA. You chose MDA solution.
Solution, yeah, sorry. Okay, so
Solution of MDA in what?
water solution. H2O.
Water.
Yeah.
Okay. Right. Very good. Okay. What happens when you hit water with a gas stream at 150 Celsius?
Wouldn't it vaporize?
Well, it would tend to vaporize. Yes. Do you want that?
No, you don't.
No, you don't. No. Okay. Right. Now, I'm not sure if I said this last week. I may have done, but or I may not have done. But absorbers work well at low temperature. They work well at low temperature because absorbers are about transferring a gas into a liquid. Right? So you want something that's in the gas phase to go into the liquid phase. That is favoured by a low temperature. Are these low temperatures? No, because you're even high enough to try and drive the solvent into the gas phase. You're trying to drive the hydrogen sulfide into the liquid phase, not evaporate the solvent.
Yeah.
So why are you using temperatures like 150 and 85 here?
It was just a bad estimation. Just a bad estimation.
Because what we can do is increase the condenser G and then cool it down further before it enters the absorber.
Well, you need to get the lean amine temperature down, and you need to get the gas temperature down.
Down, yeah.
Okay. Now that means that you may want to change that temperature.
Yeah.
Yeah.
What would you suggest as a reasonable temperature range for an absorbent column to operate at maximum efficiency?
What are you cooling with here,
Air.
Jason? Jason.
Ambient air.
So who was that? That wasn't Jason. I didn't see his lips move.
It was me, Jerry.
It's Jerry.
Okay, Jerry. Okay, so it's ambient air, right?
Ambient air.
To what temperature can you cool stuff with ambient air?
To 25 degrees.
Yeah, sorry.
No.
Well,
On a coldish day, yes, but not always. What can you guarantee to get to on the hottest day in summer?
30s, like 35.
35, 30.
Well, 35 is on the edge of being possible. Okay.
Would you say 50s reasonable?
It's 28 or 29 plus delta T min.
Yeah. Delta T.
You remember delta T min
Yeah.
From last
from
semester.
electric course?
Energy.
Time in the
Energy
distant
industrial.
past.
Yeah.
Yes.
Okay. So 35 is a bit of a stretch because your delta T min would have to be nearer 5 than 10. But you might manage 38, 39 or 40. Using air as your coolant, which means that the cost is going to be very modest. Right? And I'm not recommending that you go to refrigeration, which is very expensive. Do you have your answer?
Yeah, thank you. Thank you very much.
Now look, this block diagram is not yet in a state for us to be able to define areas. It's not yet in the state where you can start simulations. You need to get there within days. Okay? So far, people have been very reluctant to use dockets. This has been a huge mistake. You need to spend dockets to get this sorted out.
Yeah, of course.
Okay? Now, the other thing you need to add to this block diagram are tag numbers and unique names for the blocks. If you use tag numbers, that's an easy way of delimiting the areas. So this cooler, for example, might be in area 5, in which case it would have a letter for a heat exchanger, which might be E, and then a number, a three-figure number that starts with 5. So it might be E501. Okay. If it's E401 or E406, then I know it's in area 4. Yeah. You have to propose what blocks are in what area to us, and we then have to approve it. Yeah.
Mm-hmm.
Can't approve the block diagram until it's in a better state than this. When we approve the block diagram for areas, you will then not really be allowed to change the blocks, but you can still change the temperatures and pressures based on your simulation. Is that clear?
Yes, sir.
Yes, sir.
Mm-hmm.
I think you can get there within a day or 3, but you've got to do that, and then we've got to give you the inputs to your areas so you can start to do simulations such that you can at least try and bring something in the way of a simulation to next week's meeting. So this is going to be a busy week. Now, of course, you won't have the control exercise to do, so you've got more time to spend on it. Okay, and I know POM is coming up, and there'll be a week where we just do nothing. Yeah, you need to speed up a bit. Dimitrios, did you have some feedback for them based on some of the other documents? Hello, Dimitrios. Is Dimitrios gone?
Sorry, yeah. You also sent...
I'll stop sharing.
Yes.
There are other comments on the block diagram, which I will send to you. Right?
Okay. Thank you, sir.
So, you also sent equipment sizing. So let's go through that then. You did, who did that? All of you together, or
Yeah,
was
it's a
it?
group, yeah.
It's a group, yeah. It's a group.
First of all, we split our group into areas, so area engineers, and then we did the equipment sizing for our respective areas.
Alright. So, in general, most of the procedure that you have there is logical, as far as I saw it. We will go step by step now.
Can you share your screen if you're going to talk to a document, Dimitrios?
Yes. Am I sharing?
Yes, sir.
Yeah.
Yeah, we can see it.
So let's start with the heat exchanger with some questions. So this is the procedures, one procedure as how do you select, what I can see here. So Christian?
Yeah.
What are the different heat exchanger that you are going to use?
We're going to be using tube fin exchangers. We're going to be using shell and tube. And I'm not sure of the others as well. That's
What was the first one?
Thin tube heat exchangers.
All right. And based on what are you going to choose? So where you will put a cell and tube heat exchanger, or where you will put an air-cooled heat exchanger? How do you choose?
I'm not sure. I don't do that.
Take a guess. how you will choose an equipment based on what you have a process, how you will choose an equipment, what are the main parameters that you care.
Surface area, PG.
Surface area, you read it somewhere, is, yes, correct, if that's what you want to say, is the parameter that will define how you will size it. But how do you choose in general if you will use what kind of heat exchanger are you going to use? There are different configurations and types.
I read up on this part. Yeah, mine's blank. Mine is blank.
I think the point is that this is the first decision you have to make, isn't it?
Yeah. It definitely depends on whether you're heating or cooling, and then you go look at the delta T that you're dealing with.
What I was trying to say was the amount of H2S in the stream. Because if there's a high concentration of H2S, then we can't use like a particular heat exchanger. So for like
how that will affect the amount of forget the current process. Before we tell you the answer, forget the current process. We are not doing this process. You want to choose between two equipment. What are the main? You are in a chemical plant. What are, based on what are you going to choose the appropriate heat exchanger, the appropriate equipment? So what are the main parameters?
So would it be when we're dealing with either a gas or a liquid?
Forget that as well, because we don't want that. I mean, we are talking about that. We told you need to consider about these two parameters. The main parameter. If you look at your block, yeah.
I think there's a small amount of merit in what Jason's just said, which I'll come back to later. But I understand where you were going, Demetrios, so you carry on.
Anyone who wants to try and answer, doesn't matter if it is right or wrong. Say it so you will remember it from now on. So
shall I answer? And see, let's see whether or not you and I are on the same wavelength, Demetrios, okay?
Sorry?
Then they might learn something, right?
What
My answer is I'm going to choose whichever is the cheapest.
One, yeah, that makes sense. I would go more in terms of performance, one, rather than cost. Then I would go in terms of which one is more robust. But the main thing that we should check is the operating conditions, whether that the temperature and pressure that we have at this particular point that we want to put a heat exchanger, the heat exchanger, our equipment, can operate at these conditions. This is the most important thing. If you want to put a device, any device, regardless of whether this is heat exchanger, that you cannot put it there, then you will have something wrong on your whole process. So temperature and pressure is the most important thing that you need to check, whether you are within the operating conditions. All right. Now, once you select, I saw here, do you still see my screen?
Yes, sir.
Yeah. I see you have a procedure here. Now, you said cell and tube heat exchanger, you said air-cooled heat exchanger. What is the main difference between those two? You identified here. What is the main difference? One of the differences?
Air-cooled heat exchanger is usually between gas and gas contact, whereas shell and tube isn't it usually liquid and liquid or gas and liquid. Okay, sorry, liquid and liquid. Shell and tube heat exchanger. That's what I was thinking. And also because it would be more ideal to use air-cooled heat exchangers because the ambient air, as a cause, is free, so we can just use ambient air to cool it down, and we don't have any cooling water available. So
Yeah, okay. When you don't have cooling water available, this is a reason that why you are using the air-cooled exchanger. What about the flow configuration?
counter current.
Is where?
Sorry, it would be cross flow.
Is where?
Sorry,
Cross flow is for which one?
the air-cooled heat exchangers.
Air-cooled, they operate in cross flow. And the
Yeah.
cell and tube?
Counter current.
Counter current. Alright. So you have here.
The difference here between that I think we need to clear out. There are heat exchangers where you are contacting two process fluids. You can't use an air-cooled heat exchanger to contact two process fluids.
Mm-hmm.
Yeah.
Okay? The only coolant that's available to you is air. So there are two kinds of heat exchangers that we've now identified, one of which is a process-process heat exchanger, and the other which is an air-cooled heat exchanger. The two are mutually exclusive.
Yeah.
Okay. Thank you.
Alright. Then you have here, what time is it? For 10 to
10
3.
minutes to.
We've got 12 minutes left, Dimitri.
Okay. So let me go through that. Then, yeah, okay, correct. This is the right procedure. You need to take into account when can you use the temperature difference, that one here, the logarithmic temperature difference.
So wouldn't it be different if we're condensing, if there's condensation, evaporation taking place? Because then we have to do the mean temperature difference instead of log.
All right, and how you will decide whether you can take the other, the one or the other, based on what?
Based on the temperatures which the heat exchangers are operating at. So if the temperature causes the gases to condense and the liquid to vaporize, so then we can't use a log delta T min, so then we have to use the mean temperature differences as a delta T for that heat exchanger.
You will need to get first for your heat exchanger the heat curves.
Heat curve,
How
yeah.
that will help?
So from the ChemCAD, yeah.
So what the heat curves will tell you? The heat curves might be what? Might be linear or what?
That's it.
Or
Exponential.
non-linear.
Or non-linear.
And depending on that, how you will, what strategy are you going
So
to use?
if we have heat curves that are linear, then you can use the logarithmic mean temperature difference.
Correct.
And if they're not,
If not,
if not, you have to
Plus the
you have
mean
to
temperature
divide,
difference.
or you have to divide the curve up into sections that are almost straight, and then use that to
you divide what?
Yeah.
You
divide the heat curve up into sections that are almost straight, and then use
correct. And then add them all up and
Yeah.
have the overall,
heat transfer coefficient.
the overall, yeah, and then the area.
Oh, sorry.
Let me continue.
Can I just jump in? Because I think I saw there is a danger with these equipment sizing calculations, which is you need to understand that there is process design and there is equipment design. And the book will not be clear, any book will not be clear about the difference because it's a University of Surrey difference. And the University of Surrey difference is that you just need the method to get the sizing parameter. Okay? So for heat exchangers, I don't want you calculating overall heat transfer coefficients. That's for equipment design. You select an overall heat transfer coefficient from a table and calculate an area. And that's it.
Mm-hmm.
But in the
Okay.
case of a shell and tube heat exchanger, would we not have to determine how many shell passes are there, how many tube passes?
No,
Really? Okay, all right.
just need the area, mate.
Okay.
Good.
Now, in equipment design, if you're designing a heat exchanger, then of course you'll need all of that and a lot of other things as well. But we haven't got there yet.
Right, okay.
Okay, so it's important that you realise that you are just putting down in this document only the stuff which gives you the size, which means that it's a clever thing to do is to start by saying the sizing parameter for this piece of equipment is. Okay, and that then focuses the reader's mind and your mind on what you are trying to calculate. Okay?
Yeah.
So I see there's correlations there for heat transfer coefficients on that page. Okay?
Mm-hmm.
That's all equipment design. Okay, you pick a condensing heat transfer coefficient from the table. I'm not seeing any extracts from tables here. Okay, there are tables in Coulson Richardson Volume 6. I think Dr. Short gave you a table. There's a table in Perry's Chemical Engineer's Handbook, etc., etc.
Yeah, so I put a link of that in the...
Yeah, but that's all you need.
Yeah.
Okay, and the other thing to say is that you'll probably get the heat load from the simulation. So
Right, but
you
wouldn't we need like...
don't really need a method for Q unless you're the process coordinator and doing checking calculations.
But wouldn't we need like the approximate flow rates for that in order to actually simulate it on ChemCAD?
No, ChemCAD will calculate flow
The
rate.
heat you. Yeah.
Oh, okay.
ChemCAD does mass balances, it does heat balances, it does the whole lot.
Yeah, my bad.
Okay. But this seems to be a pretty full document. Somebody's worked really hard. I did have a slight problem with the heat transfer thing where it suddenly mentioned plates in the middle of a method that was meant to be about shell and tube heat exchangers.
I don't recall that.
First page.
First one.
Oh, I think it was regarding the distillation column. Is it what we're talking about?
No, there. The design procedure is similar to that for shell and tube heat exchangers. Well, this is meant to be about shell and tube heat exchangers, isn't it?
Yeah.
Go up a bit, Demetrios. That is a design procedure for a plate heat exchanger. I know where it comes from. I even know which book it comes from.
Yeah.
And there isn't a reference.
Yeah. It's so I stated at the bottom, Coulson Richardson, Volume 6, 4th edition, page 758. It's right.
That looks to me like a scan.
Yeah, but the
Yeah,
reference
okay.
is at the bottom.
Well, that's okay. That's a bit clumsy.
So, no.
But your introduction doesn't say here is the method for a plate heat exchanger, as far as I can see. And this is what Demetrios, was getting at. Is that your first question is what kind of heat exchanger are you chosen to use, and on what criteria? That is the first thing you have to do. And then if you want to do a place heat exchanger, that may be a pretty good method. Okay. But it's not the method you use for a shell and tube heat exchanger.
Yeah.
Okay.
So before we close, let me go a bit fast through what I want to say, and of course we can talk again Thursday in my office hour and Friday. So what you have to do now is continue what you are doing here and have it like this. You have heat exchangers, you will have, as you said, condensers, reactors, pumps, Scott reactor, how you are going, reheaters, stacks, everything. So what you want, what you need to do is write them down and say that we have heat exchanger, condensers, and that. For that, the sizing parameter, as you said already, is the area. Then for the reactor is what? What do we care when we have a reactor? What is the sizing parameter?
Volume.
Think a bit.
Catalyst. The amount of catalyst.
Well, that's one of the things, yes. Because the other thing is
the volume.
Well, sadly not. If you go to a costing book, it won't say volume, I'm afraid.
Tube sizing for if it's a PFR.
You're guessing.
The volume, you will need it, but you will need it to calculate something more important, which is the sizing parameter. Because the volume is the volume that you have inside your reactor, but the sizing parameter is not only the volume for that, for your catalytic reactor.
Size of catalyst. Is it the size of the catalyst?
How the size of the catalyst would define?
No, you're guessing. You've got to go to a sizing book and find out what the sizing parameter is. It's no good guessing.
So have it as a list, and we can discuss it through the office hour. I mean, have it as a list that. And then, as far as I remember, we talked last week, it was your group, about COMAC procedure, and we said that you need to do assessment for all the components present in the process. Have you thought about that?
Yes.
Okay, then we can discuss that and see. We said to identify and classify in terms of potential hazards, and to discuss it further here or in the office hours. Have you done that?
Sorry, can you repeat your question? Sorry.
We said that you need to assess all the components in the process, or try to, and to identify and classify them in terms of the potential hazards. That's what we said in the previous meeting.
Yes.
I'm going to leave and join the next meeting. Come and join me when you can, Dimitros. Okay.
Yes.
Should I continue on?
Yes, please.
Yeah, I tried to do all of them, but then when it came down to the scoring, there's it doesn't really have any scores for majority of them. So only the